All right, in this video, we're going to be talking about the traveling salesman problem as well as nearest neighbor. So let's get started. So the traveling salesman problem is literally, like it said, you are going to be dealing with, as you can see right here with this weighted graph, it's basically a map, and in this context of in the context of this graph, you're dealing with a map where you have some cities, but notice something different now. Now you have a bunch of numbers that are on each edge. And what that means is these are now the weights of each graph. Now, the way that you would read it, again, in this context, and it's not very hard to see, and that is like from St. Louis all the way to Chicago. Notice that you're on this edge where it's 270. So it would be, I guess, I'm assuming because it's not labeled, but I'm going off the assumption that it would be 270 miles. All right, same thing from Chicago to New Orleans, you're going 910 miles. So when it comes to traveling salesman, I mean, very similar. A traveling salesman has to deal with a map. That's what these graphs are going to represent. Now, the traveling salesman problem is basically what you're doing is you're going to be analyzing a graph, a weighted graph, and you're going to try to find a route that visits each city exactly once, but you're finding the shortest possible route. Sorry about that. I should have had that first. So you are going to find the shortest possible route that visits each city exactly once. So you're going to do more analyzing of a graph as opposed to as opposed to creating. All right. So here is our first little example here. Now this is the final product. So what we have here is our map that you'll be starting out with, and then you also have a tree diagram which you'll be creating. And all the tree diagram does is just represents all the different ways that you could start at St. Louis and visit all of the different cities. Now, again, when you're dealing with Hamiltonian circuits, there's many possible routes. So that's why we have at the end, if you look, you have basically 6 final destinations. All right. So all these different routes, all these different cities will take you to different mileage. So, like for example, if you go to St. Louis, New Orleans, Chicago, Minneapolis, St. Louis, that's one route. All right, that's one way to go. But if you were to go something like um, St. Louis, Minneapolis, going all the way down to New Orleans, Chicago, and back to St. Louis, that's another way you can go. And all of this is in this particular graph or tree diagram. All right. Now, I'm going to talk you through how you create it. All right. So let's get started with this. All right. So the weighted graph below. All right. So this graph right here represents the distances from buildings at a local university. Create a tree diagram that displays all the possible routes. Now, if you notice, the root of our tree diagram is math. So this is going to be our starting point. This is where all of our Hamiltonian circuits will start. Now, if you notice, it's a Hamiltonian circuit, so if you notice, it'll also end at the math building too. So notice that the M starts the graph, the M's at the bottom in the graph. So remember, Hamiltonian circuits, you start and end at the same vertex. All right. Now, just again, just kind of looking here, starting at math, notice how in our tree diagram, it branches in 3 directions. The reason why it branches in 3 directions is because if you go to the graph, you could either go to the gym, you could go to science, or you can go to art as your first destination. Okay? So every time you have a choice, your tree is going to branch off. Okay? So, like for example, what I want to do is focus on, and let me kind of clean this up a little bit. All right. What I want to do is focus on this right here. Let's say if we were to go to math and then we were to go to the art building. All right. So if we were to start at math and if we were to go to the art building, notice we have 2 choices. We can either go to science or we could go to gym. So there's 2 places that we could do or we could go. So we are going to label that accordingly. So we could go to science. Oh, let me try that again. We can go to science or we could go to the gym. Notice my tree, my branch split because I have a choice. Now you are going to fully investigate every single possible route. All right. So what that means is, let me kind of erase here and let's say we decided that on our tree, I'm just highlighting here just so you know what I'm doing. Let's say if we were to go to science. So if we were to go to science, where would we have to go for our next Hamiltonian, as we're completing our Hamiltonian circuit? We would have to go to the gym, and then we would go back to math. All right? So if I was to create this branch, after going to science, I would have to go to the gym, and then I would go back to math. So this would be the route in the tree. So this would be my route in the tree. So it would be math, science, gym, math. All right. So notice what's highlighted in the graph itself is highlighted in the tree. All right. Now, let's say we wanted to go to math, to art, to gym. Let's say we want to go that route. So if we were to go to math, to art, to gym, if we were to go in that direction, which way would we have to go now? We would have to go to science, and then we'd have to go back to math. All right, I had to pause the video for about 5 minutes, so I kind of forgot where I was at. So we go to the gym, we go back to science, and then back to math. All right, so that means we would go to science, and then we go back to math. So again, using coloring just to kind of make it stand out a little bit. Those are two of the 6 possible routes that can be created through this map here. Now, once you create your route, you need to then go back and do the times. So what I mean by that is, let me kind of clean this up a little bit just because it's needs to be cleaned up, I guess. And of course, I can't clean everything up because it'll mess up. All right, so for example, when we start putting times on our branches, from math to art was 9 minutes. From art to science ends up being 5 minutes. From art to gym ends up being 2 minutes. From science to gym is 7 minutes. Gym to science is 7 minutes. And then gym back to math is 10 minutes. And then science back to math is end up being 4 minutes. So when I add all this information up, all right, so when I add all this information up, so if I was to actually add up all of the first, or I'll just stay in colors here. If I was to add up all of this entire route, 92714, so 927, 97, I'm sorry, 9274, that would be 22 total minutes. It'll be 22 total minutes for the green path. All right. Then from here to do the yellow path, which again, I'm just highlighting just so you can kind of see it because the yellow coincides with that. That would be a grand total of 31 minutes. So two circuits, each starting and ending at math 2 different times. Now, from here, you would then continue. So let me kind of clean this up. Okay. So let's kind of keep going with our tree here. So let's play the what if game. And let me use another color here, blue. So if I was to go to math and then gym, so on my chart, if I was going to go to math and gym, notice I have 2 choices. I can either go to science or I can go to art. All right, so I can go to science or I can go to art. Now, we'll just go ahead and do art here. So that means when I start filling out my chart here, art, I can go to art, or I could have went to science. But I'm going to keep doing what's already highlighted, and I'm going to go to art. And then if you notice on my chart, I would have to go to science, and then I would have to go back to math. So I would have to go to science, and then I would have to go back to math. Okay? So let's go ahead and just do this chart real quick. So math to gym is 10 minutes. Gym to art is 2 minutes. This will be 5. And then science to math would be 4. The biggest challenge of this is not necessarily, which is 21 minutes. The biggest challenge of this is just the fact that it's just monotonous. That's really what it is, because you're just doing a thorough examination of all of the potential circuits in this. All right. So let's go ahead and do purple. So let's say we did math to gym to science. Let's see. So math to gym, and let's say we went to science. We would have to go to art, and then we'd have to go back to math. So to fill out this branch, we would have to go to art, and then we'd have to go back to math. All right. So gym, math to gym is 10 minutes. Gym to science, that's 7 minutes. Science to art is 5, and then art back to math is 9. And you would get 31. Now, pause for a second. Notice that 31 is represented twice. So when you fully investigate this graph, you're going to have some repeats. And the reason you're going to have repeats is this. All right, so pay attention real quick. Notice how on the purple route, we went to math, to gym, to science, art, back to math. Okay? But notice on this yellow route, we went to math, to art, to science, to gym, to math. So what you have is a repeat, but it's in just in reverse order. So when you are doing this as a self-check, you know that you should have duplicates. All right? You should have duplicates. Now, just to kind of speed this up a little bit, math to science, I'm going to go ahead and speed this up a little bit just because of time. I'm looking at the time and we're running long. So art, gym, you can go to gym, go to the art. All right. So this will be 4, 5, 2, 10, 7, 2, 9. So when I add everything up, this ends up being 21. This ends up being 22. Again, self-check time. As you're building this, notice that you have duplicates. There's a 22. There's a 22. Here's the 21. Here's the reverse 21. Okay? So again, that's a self-check. When you have duplicates, you know you're doing it right. Now I'm just going to make a mistake here. Let's say, for example, this ended up being, I'm totally making this up. Let's say this ended up being 27. Well, I would know that this would be incorrect because there's no other 27 in my tree here. So remember, everything has to be duplicated. All right, so again, if you're getting one number and you don't get the duplicate, then obviously what we have is a problem. So you might want to check your math on that one. All right, so let's bring back to 21. Now, from here, let's go ahead and answer a couple questions, or in this case, a question. Your first period college class, your first period college class is math, and the class is 4 hours long. The teacher will give you 30 minutes, a 30-minute break, and you need to drop off some papers at the gym, science, and art. Um, do you have enough time to make all your deliveries? Well, based off of this, you do have time. You know, you could go this route, you can do this route, you can do this route, you can do this route. So based off of what you created, you have information that backs up the fact that yes, you can make all your deliveries and get back in time before the teacher starts teaching again after break. All right, pretty simple. Now, lastly, is what we have is the nearest neighbor algorithm. So with a nearest neighbor algorithm, you are still creating a Hamiltonian circuit, but you are now going to have a little bit of direction on how to create it. So it's a circuit that is created based upon a vertices or a vertex's nearest neighbor. All right. So best way to do it is to show you. Now, if you remember, it says find a route using nearest neighbor. Start at St. Louis. All right. So we are starting at St. Louis. This is our starting point. And with nearest neighbor, you'll always be given a starting point. All right. Now, look at your neighbors. You have Minneapolis, Chicago, New Orleans. What is your nearest neighbor? Well, it is the city that is 270 miles away. That's closest, which is Chicago. So now we're on Chicago. Now from Chicago, we got to find who is our next nearest neighbor. Well, Minneapolis is 400, Chicago is 910. Well, I know 400 is a lot less, which means it's closer than 910 miles, which is Chicago. Now, when you're dealing with the nearest neighbor, you think to yourself, well, it's in the name nearest neighbor, then I could just simply go straight to St. Louis because that's my nearest neighbor. Unfortunately, you've got to create a Hamiltonian circuit, which means all of the cities must be visited. So what happens is you run into a situation where you run out of options. So Minneapolis, you would have to go all the way to New Orleans because that's your last option. And then from here to complete the circuit, then you'll go back to St. Louis. So that would be your nearest neighbor circuit using this example. All right? Using math, same exact way. So if you remember the one that we just did, if you were just going to all the buildings that were closest to you, which one would you go to first? Let's see. Art's 9 minutes away. Gym's 10 minutes away. Hey, science is 4 minutes away. That's my nearest neighbor. 4 minutes. From science, I can go to art, which is 5 minutes. I can go to the gym, which is 7 minutes. Well, art is the closest neighbor. So from here, I have to complete the circuit. So even though the gym is closer, I would have to go to the gym regardless because I have to complete the circuit, which means I have to go to the gym and then go back to math. And that's your nearest neighbor. Now, maybe I went too fast on that. So let me just do one that's in the back of your worksheet here. It says start at vertex A. So starting at vertex A, this is a little bigger map, but you're still going to the nearest neighbor. So I can go to B, I can go to C, I can go to D, I can go to E. Well, which has the smallest weight? Well, that would be B. So now I'm on B. I can either go to C, I can go to D, or I can go to E. Well, again, what is your nearest neighbor? Which means what has the smallest amount of weight? That would be D, which is 41. Now, once you get to D, again, I can either go to E, which is 53. I cannot go back to A because I've already gone there. So my options have been limited a little bit. I can go to E or C. Well, C is my nearest neighbor for 28. And then once you get to the second to the last city, or in this case, stop here, you're running out of options. So I can't go to B. I cannot go to A. I have to go to E. And then from E, I'm just going to finish out my circuit like so. All right. From here, A, again, starting at vertex A, my nearest neighbor is C. From C, I have B, I have D. Well, B is closer. For B, I'm getting to that point where I'm running out of options. I have to go to D to complete the circuit here, and I would have to go to A to finish it out. So that would be my nearest neighbor. So, and then you would answer a couple of questions. What is the nearest neighbor? So let's say use the nearest neighbor algorithm. The other graph is extra practice. Use the nearest neighbor. I'm guessing I would use this guy right here. Now from here, then we get into some pretty simple stuff here, like what is the weight of the nearest neighbor? Then you just add up all the things that you use. So I think 37 I used 41, I used 28, I used 33, and I used 46, and I would just add that and answer whatever questions I'd had to deal with. All right, but that's pretty much it, and I'm going to cut it off here because I'm getting close to the 20-minute mark, and that is too long for a video. Thank you for watching. I hope this all made sense.